Okay, class, let's continue. So we discussed what is the Mason's rule. Um, Now let's see some examples, but before doing new example, let's still look at this old example we have done a couple of times. So, but here we're gonna use a new method. It's not too complicated, it's still very straightforward, but I'm gonna work on this block diagram a little bit. Um, so as we have done earlier, right, this is my y of s, and we know here the input signal here is my y of s over G4. This is what we have done earlier up there. Now, or let's say, so here the input to the H2 block is y over G4. This is what we have derived. Now, now, if we look at the connection, of course, the two blocks downward with H1, H3, the starting or the input is always y here, is always also y here, but input to H2 is a little bit different, which make it not very convenient. But since the connection is relatively simple, right, um, it's y over G4 is only one block away from G, so it's actually possible for me to redirect the connection to, it will be more ideal to do this, to start the block from here, from y. But if, of course, if the signal, the original, if the signal at the input is y, but eventually I want y over G4, what do you want? What do you need? You connect it with a block with transfer function 1 minus G4 to make this happen. Right, and there you have this one. Now, is it better? Of course it will be better, but is there anything more we can do to make it simpler? Yeah, we can redraw this a little bit prettier so that you will see how this can be further utilized. Okay. And by doing so, instead of having all of these y arranged in this manner, I'm gonna again modify this a little bit so that we can expand the discussion a little bit. So temporarily remove these points here, this point here, and maybe. And this is what I'm going to do. I'm going to do one here, and then it doesn't really matter where you split the signal or where you send the signal, it will be the same y, right? But I'm gonna do the connection like this. So you have all of these dots represent the same signal y, but when I do that, instead of having three loops intertwined with each other, now I can view this in a slightly different manner. I can view this as an inner loop, right? And I'll have, this is my second layer, right? Where the inner loop is just part of that. And then you have eventually the outer one, which represent the entire system. Now, that being said, this red guy is something we have. Let's focus the interloops. So let me G4 here, right? And then this is my H1. That represents this one. Now, what's the transfer function of this? This is what we have done earlier, right? This transfer function, or this is equivalent to direct path, G3, G4. G4, H1. And you have one direct path, one loop, so we don't have to worry about multiple direct paths or touching, non-touching loops. And of course, this loop touches your direct path. Okay? Now, this is the inner loop. Let's look at the boxed version. That will be what? I will draw this and you would immediately see how we can utilize that. Safer. Nice. And then G2. And then G2 connects to this inner loops. And I know what the inner loop looks like, so I can just replace the inner loop with my right? This is what I just already derived. This inner loop, and of course this connects to the outside. On top, what we have H2 and 1 over G4. I didn't alter any connections. There's still the connection, but I just replaced the inner loop, which I figure out the transfer function and fed it in here. So this is the mean. Again, a simple feedback control loop, and I can calculate the transfer function. Right? The transfer function will be what? Again, direct path. G2 this is my direct path. And then 1 minus loop gain, since come back with a negative sign, so it will be 1 plus, and everything multiplied together. Right? So it will be G2, G3, times H2 times 1 minus G4. And of course, eventually this G4 will cancel each other. And then we can box this as a bigger block. You used to have 1, 2, 3, 4, 5, 6 blocks in this purple box. Now you have one aggregated box, which makes things easier. Right? If you want to simplify this, we can further simplify this. How do we simplify? We multiply, row. G2, G3, G4 on top. And will be what? Will be 1 minus G3, G4, H1. This would multiply by 1. Right? And let's see how, if you only look at the 3G4, and we have them G2, G3, G4. And what about the loops? In this purple box here, again, we only look at this, guys. So we have 2 loops. H1, so 1 minus loop gain. The other loop will be G2, G3, G4, 1 over G4 and H2, so that's the other loop. So G2 times G3 times G4, sign, so you have minus, negative number will be plus. So again, if you look at the purple box here, the transfer function is still direct pass over 1 minus the loop gain. You only have one direct pass. You have two loops. The two loops are touch the direct pass, so the simplified version still applies. Now we can do it, one last time to the outer loop. Plus minus, we have G1 as the first block connected to this purple box, so I replace that with what we have above. This big one, G2, G3, G4, 1 minus. And then the loop come back with H3. So this is still the original system. Okay. Still the original system. Purple box here with the transfer function I further derived. Okay. So the first step, I figure out what this back into the purple box, figure out what's the transfer of the purple box, and then plug in the purple box into the outer green box. Step by step, every time I only have one loop involved, transfer function, same idea, right? You have one loop. This is the example we have at the beginning of this chapter. Shorter, actually. 1 minus G2, G3, sorry, G3, G4, H1. All of them, G1, G2, G3, G4, over 1 minus G3, G4, H1, plus G3, H2, G2, G1, H3 multiply, the middle big one. Of course, you organize the terms, again cancel the denominator on both sides of this fraction. On top, above, and then here again you have 1 minus G3, G4, H1. This is 1 minus the loop gain of the first loop, plus G2, G, and then eventually, I'm sorry, here to be 1 plus, since it's minus a negative sign coming back here, so it should be a negative sign. So it'll be plus H3. This happens to be the loop gain of the outer loop. And we have seen this. This is exactly the transfer function we derived using the simple signal method. So either one should work. You play with the intermediate signal, that's fine. You use the Mason's rule, that's fine. This is you can view this method number 3. This is still, sometimes called block diagram algebra, but that's not rearranging the blocks, right? We arrange this G4 block medium loop, middle loop, and the outer loop to have this small subsystem that we can utilize in a derivation. Okay. So this is our third method. And of course, as far as convenience is concerned, Mason's rule is the most convenient, and the block diagram rearrangement can also will work. Okay. So and I'll demonstrate all three methods to solve that problem.